So this really follows on from the integration. We've seen a whole heap of integration techniques. So a logical application to look at is the volumes. That's one of the first things we did with integration, I suppose. Now, how we did it in 2-unit/3 unit was this idea of discs and washers, but we didn't really go into it as much detail as what we're now about to. So let's just have a look at the idea. This technique is whenever you want to slice the volume perpendicular to the rotation. So we're assuming it has a circular cross-section. So let's just look at a general one going about the x-axis. So some function, and it uses the idea we want to go from A to B, and we're going to rotate that shape around the x-axis, but I'm going to slice it up. And because they're all circular cross-sections, I know that when I slice it up, each slice, if you like, will be well, theoretically it's a cylinder. Although we want the thickness of that cylinder to be very small, but theoretically we get a cylinder. So if we were to rotate that, there's our slice rotated round, and we get our cylinder. Thickness is delta x. We know how to find the volume of a cylinder. So our radius would be whatever the y value is. But we want it in terms of x. So whatever the thickness is, that delta x, which will later become dx, so we're doing it with respect to x, we want everything in terms of x. So the radius, whilst it's the y value, well, I'll make it whatever function x is. And so we know the area of the cross-section face will be pi times the radius squared. So to get the volume, we'd multiply it by the thickness. Now this is where the difference is between 2-unit and 3-unit as opposed to what we do in 4-unit. In 4-unit, they want to see that delta V equals pi times, and how you got it. I think it's a good idea to draw this actual slice itself and then show the slice. Okay? Because otherwise, what we'll see when I do an example, it's just a 2-unit question. Why would they be asking a 2-unit question in Section 2? They're not really interested in the answer, and all. It's how you got there. Do you know how this works? And so the way it works is, of course, we're going to sum up, we're going to add all of these slices together. So we want the limit as that thickness is approaching 0, and we'll go from A to B of pi times function x squared delta x. Now that becomes the integral, and we saw that back when we worked out the area formula, if you remember. Essentially it's the same thing, because I can factorise the pi out, that's a constant. And so I'm saying I've got the sum of all these things, delta x, and as we saw back when we did area, that just became the integral from A to B. So it is okay to jump from the sum straight to the integral. But don't go straight to the integral, because as I say, if you do, it essentially turns into a 2-unit question, and that's not what they're interested in. So if you go around the y-axis, well, same sort of thing is going to happen. We want to go perpendicular to the rotation. So this time my slice is going to be horizontal. So the thickness is delta y. So I want everything in terms of y. So there's my disc. Thickness delta y. Pi times the radius squared. Well, that's the x value. That'll be, well, it'll end up being some function of y. I'm going to have to rearrange the function to make x the subject. Delta v, pi, and so on and so on. So it's much the same now. Then we can say, okay, well, I want to sum up all of these slices, and we get our integral. Let's do an actual example then. So we've got our upside down parabola, and we're going to rotate about the x-axis. So there is our parabola. There's a slice. We're going perpendicular, so it's a vertical slice I'm taking. So I'll just draw a picture of my slice. The radius is the y value, but I want that in terms of x, so it becomes 4 minus x squared. So the area is pi times 4 minus x squared squared. So this is what we actually call the element. So the element of the volume, or the volume element, however you want to say it. So the delta V, change in the volume, if you like, is pi times, and I've expanded it out. Whether you expand it out now or you expand it out later, it doesn't matter, but at some point you're going to have to expand that out. So we're going to sum all of these, and we're going from -2 to 2. But of course we can still use symmetry. So you notice on my integral, I've changed it twice to 0 to 2. We can still use those ideas, that's fine. And as I say, it really just becomes a 2-unit question now. Add 1 to the power over the power, sub in. So we don't want to be making silly mistakes there, because if you like, that last mark in a lot of cases, that's actually the gift mark now, rather than the first mark being the gift mark. It's the actual evaluation. But the nice thing about this is we don't have to go around the x-axis now. I can go around any line I like, because they're same shape, but instead of going around the x-axis, we can rotate around the line y equals 3. So if I draw my slice, before I draw my slice, of course, I'll have to find the points of intersection. I'll need to know those points. But there's my slice, and I'm rotating around. I still get a disc, but now my radius is not the y value, it'll be y minus 3. So y minus 3, I want it in terms of x, so it'll be 1 minus x squared. I suppose the same thing could have been achieved by getting the whole shape and shifting it down to the x-axis and doing it around the x-axis. Yeah, I suppose that's an alternative way of doing it. But hey, that saves doing all this. I can just do it all in one hit. So it's 1 minus x squared is the radius for this one. And there's my element of volume. And now, as I say, we write the sum down, because that's the key piece of information. We're saying, okay, I know that to get the volume, I'm going to sum all of these volume elements up, and we get add 1 to the power over the power, and there's our answer. So in a lot of cases with these, the actual integration, whilst we've looked at a stack of integration techniques, it's not too difficult to start off with anyway. Okay, we're going to rotate between y equals x squared and x equals y squared. We're going to go around the y-axis. There's y equals x squared. There's x equals y squared. We're going around the y-axis. So my slice, find the point of intersection, of course. So my slice is horizontal. There's my tiny little slice in there. Thickness is delta y. So we want everything in terms of y. This is what we call a washer. Okay? Now, if you've ever done any bit of woodwork, so when you put a screw in, they like a washer to put between. Okay. So we've got an outside radius. So the outside radius would be going to the red curve. So I've made it red. Clever, hey? So, but I want it in terms of y, so it's y to the power of half. The inside radius is going to the blue curve. That's already in terms of y. So we go x is y squared. And so it's the big one squared minus the little one squared. I guess the main thing we could do wrong there would be to do the subtraction first and then square it. So it's not a binomial product, it's the first one squared minus the second one squared. And so tidying that up, again, the integration doesn't become too bad. So we're going from 0 to 1 is our sum. Add 1 to the power over the power. Sub in 3 pi on 10. Here's an HSC one. Interesting shape. And they wrote it as x plus y squared equals 0. I don't know whether that threw people or not, but really, if you look at it closely, that's just a parabola on its side. But they've written it as x plus y squared equals 0. So all of a sudden it looks unfamiliar. People, what is this shape? All right. We're going to rotate. So what have we got? We've got x equals 1, y equals 1, y equals minus 1. But we're going to go around x equals 4 and rotate. We're going to end up with, it's what I would call a grommet. Yeah. You ever seen those spongy, it's like a washer, but they're spongy. No? Okay, let's think of another shape. The thumbtacks. Except these ones would have a hole in it. That sort of shape we're going to get. But you're right, someone said a bit like a ring, but it'd be a weird ring. All right, so the first thing that gave us a big hint in this question, hey, the area is going to end up being this, so let's just prove that. So it's a washer that I've got. I want everything in terms of y. I'm going to have an inside radius and an outside radius. Let's go back to the diagram so I can work that around, because here's where I've got to be careful. Remember, it's around 4 I'm going to. So the inside radius would be going to the straight line y equals 1. And the outside radius would be going to the parabola. So the inside radius is 3. The outside radius will be 4 minus the x value. So it ends up being 4 plus y squared. So we're going to be real careful, because it's really tempting to say 4 minus y squared because you're over in the negatives. But the y value that is substituting in is negative anyway. And if you think about it logically, it's got to be bigger than 4 because you're going past the y-axis. So it's always going to be, that's why I put the first line in. It's always going to be 4 minus whatever the x value is. Well, if that x value ends up in the positives, yeah, I'll get something that's less than 4. If it ends up in the negatives, I'll get something that's bigger than 4. So always 4 minus the x value. So let's put those in. Outside radius, 4 plus y squared. Inside radius, 3. All right, square the first one minus square the second one, and we come up with the answer that what. Okay, from there, hence find the volume. All right, well, I can now find my element of the volume. Pi times that times delta y, which means the sum is, be careful because we're going with respect to y, so it's minus 1 up to positive 1. Again, it is symmetric if you look at that diagram. So I can go twice from 0 to 1. Add 1 to the power, over the power, and we get the actual answer. Ooh, several questions there. Okay. So what you've got to be careful with discs and washers, because this technique we saw in 2-unit and 3-unit. Okay. We're going to look at other techniques which allow us to do greater volumes because we can use other ideas. But if it is one that I've asked you to use using discs and washers, then make sure you set it up. It's very specific in the syllabus. They say that they want to see things like, expressing the volume as a limiting sum. So that sum expression is very important, and how you got there.